permanent magnets repel when facing each other. I have in my hands 2 small neodymium permanent magnets, each weighing 45 grams. And it's quite difficult to press them together. They're quite fun to play with. But imagine if we took something 40 times bigger than this. How much force would it need to push them together? And maybe we can build something interesting as a permanent magnet suspension chair. Watch this video and you'll find out. Let's start small. 2 45-gram permanent magnet cubes start flying at each other in distance of 10 centimeters. The closer they move, the harder they accelerate. Now let's introduce a large permanent magnet into the plane. Iron objects are attracted from 15 centimeters apart. The small magnet now is drawn in from 25 centimeters apart and flies into the wood with even more energy. Note that I use a wood to protect the magnets from chipping and breaking, since with these sizes the final impact is just too powerful. A fancy alternative is to use an aluminum block, so when magnets are moving, the induced opposing magnetic field acts as a damper. So when slowed down, we can observe a linear nature of the attraction. Although this is a topic for a different video, I have to show you how these large permanent magnets behave when large conductor is present. A moving magnet creates changing magnetic field, which induces eddy currents in the metal. The magnetic field caused by induced currents oppose the external field by permanent magnet. So when I move the magnet swiftly, whole 24 kg aluminum plate can be drawn or spun. But the most exciting demonstration of this is drawing the magnet between 2 plates, and suddenly magnet is floating in the air. You just saw gravitational energy transferred into electrical, which then is dissipated as heat, simply warming the plate with each magnet drop. Now let's get back to magnetic suspension experiment. First, we need 4 large permanent magnets, which luckily we have in our laboratory. To understand what are we dealing in terms of forces, I run a numerical model which calculates force between the magnets when they're pushed together. Theory states that the repulsion force when magnets are completely pushed together is 2,800 newtons, or 285 kilograms. And we're going to use 2 pairs of them, so double that. To accommodate such forces, we needed to build a device that allows free movement of magnets in a vertical direction and ensures no sideways movement or twisting. The demonstration device has 2 magnet holding platforms that are built from plywood and each hold 2 magnets. These platforms are connected to rails with sliders, which allow movement with only 1 degree of freedom. We had to avoid metals for building materials since they can be magnetic or conduct electricity. Yet the frame on a platform has to be strong enough to hold half a ton of weight predicted in the calculations. And here's the end result. Upper platform turned out quite heavy. Together with magnets it weighed 35 kilograms. So distance in equilibrium is just over 6 centimeters. It can easily support my weight when I sit on it, or even when I start jumping. Overall, the suspension, if you can call it like that, feels a lot harder than expected. If we wanted to make it softer, one way would be adding more magnets in series, like I have shown in the example. This different system acts like a magnetic spring. One surprising thing here was that I could apply forced oscillations with my hand and push the magnets together for a moment of time. That's possible because I'm applying energy in each oscillation like in a swing, rather than simply pushing them together. But that's cheating, and we want to do this properly. Now let's take some weights and see how much force does it take to push these magnets together. To do that, we're adding weightlifting plates, and in the left lower corner you can see total applied weight, and in the upper left corner distance between magnet surfaces. In the beginning, separation distance drops off quickly, but further we go, the harder it is to push them together. By using half of the plates, that's 200 kilograms, we have pushed surfaces together from 60 to 10 millimeters, but the hardest part was yet to come. We used all of the plates, which in total was 435 kilograms, and there still was a gap measuring around 0.6 millimeters. We scrambled 2 aluminum blocks, thus adding 35 kilograms, which increased the total to 470 kilograms. At this point, we were almost there. One pair of magnets were in contact, while other side you could still pass the paper through it. Just to be sure, we had to bring in more weights. This is a 95 kg anvil, which we put on the top of the tower of weights in place of the aluminum blocks. At this point, we were applying 530 kg of weight to the magnets, and that was enough to achieve the result of pressing 2 pairs of permanent magnets together. Now let's think about the result we just achieved. Pressing our magnets together took over half a ton of weight, or in American units, weight to 5 Donald Trumps. There were 4 permanent magnets with total weight of 7.2 kg, and it took 75 times the weight to press them together. That's impressive, and almost as much as numerical model predicted, within a reasonable tolerance. Another takeaway is the fact that each permanent magnet by default experiences internal forces with such order of magnitude. This is one of the reasons why we have size limitations on how big individual permanent magnet can be manufactured. I hope you enjoyed this video as much as I did making it. And if you want to see more videos with massive permanent magnets, subscribe and check out the suggested video on screen. See you there!